People say knowledge is power, but I would say listening is the precursor to knowledge. So, listening is very powerful. Today, we are going to solve the problem of a simply supported beam that is subjected to uniformly distributed load by Galerkin's weighted residual method. Already, we have solved the problem of a simply supported beam that is subjected to uniformly distributed load by two methods. The first method was point collocation method. The second method was subdomain collocation method. What is point collocation method? We make the residual zero only at chosen points. What is subdomain collocation method? In subdomain collocation method, we make the residual zero in an overall sense. If this is confusing to you, it should be confusing if you are listening to these statements for the first time. I highly recommend that you go back and watch the elaborated lecture on point collocation method and subdomain method so that you can wrap your mind around the concepts. If you have difficulty understanding the concepts, listen to the lectures again and again and again and ask questions. Your subconscious will provide you the answers. Okay, the Galerkin's method is named in commemoration of the person Boris Galerkin. You can see the picture of Boris Galerkin here. He was a very versatile person. He was an engineer. He was a mathematician. He was a teacher. Galerkin had very strong inclination toward political activities. In fact, in the company he was working, he organized a strike and he was imprisoned for that. He was also a general lieutenant. So definitely Galerkin was a very versatile person. But he is popularly known for this method of solving the differential equations by Galerkin's. We call them as Galerkin's weighted residual method. Okay, so Galerkin's weighted residual method, it is actually Galerkin's weighted residual method that gave birth to the concept of finite element analysis. Or if I have to tell my statement very precisely, I should say it is the piecewise extension of Galerkin's weighted residual method that gave birth to finite element analysis. So Galerkin's name will forever echo into the concepts of finite element analysis. Now let us do the problem of a simply supported beam by Galerkin's weighted residual method. So first let me draw a simply supported beam. So here we go. I'm going to draw a simply supported beam. Let me define the geometric properties of this simply supported beam. The simply supported beam has got a length of magnitude L. It has got moment of inertia of magnitude I. Remember, moment of inertia is resistance to bending. Its unit is meter raised to the power 4 or mm raised to the power 4. Okay, the beam is made up of material that has got an Young's modulus value of magnitude capital E. The beam may be made of concrete. In that case, you have to substitute the Young's modulus value of concrete. The beam may be made of steel, in which you have to substitute the Young's modulus value of steel. Okay, what is the load, the stuff that is acting on this beam? The stuff that is acting on this beam is a UDL, an acronym for uniformly distributed load. So that magnitude is Q. It may be Newton per meter or it may be Newton per mm, depending on whatever unit is conducive for you. So these are the given data. What is the governing differential equation of this particular physical scenario? Every physical scenario in this world has a governing differential equation. Governing differential equation has information stashed in them. So what is the governing differential equation? So I'm going to write the governing differential equation. It is EI d raised to the power 4v over dx raised to the power 4 minus q is equal to 0. So that is the governing differential equation. Okay, where E is Young's modulus, I is moment of inertia, V here stands for vertical deflection, transverse deflection. X is any arbitrary location on the beam measured, reckoned from the left extreme end. So that is X. It may point at the center of the beam or any position on the beam, any arbitrary location on the beam. Q, you know, it is rate of loading. Okay. Now what about the boundary conditions? Two boundary conditions are obvious. Deflection at the left extreme end is 0. Deflection at the right extreme end is 0. First two boundary conditions are quite obvious. The next set of boundary conditions, the bending moment, which is EI into d square V over dx square at x is equal to 0 is 0. Bending moment, which is EI into d square V over dx square at x is equal to L is equal to 0. So this is the expression for bending moment. If you are wondering how this expression for bending moment comes, in the derivation of the governing differential equation, I have explained how this expression for bending moment actually comes. So this is the expression for bending moment. You have to burn this expression into your brain. It is of paramount importance. Okay, what is the first step to solve this particular governing differential equation? The first step is to assume a trial solution. So here we go. Assume a trial solution. So what is the trial solution that you are going to assume? Well, I am going to assume a trigonometric trial solution. I will use a different color. So V of x is equal to a naught into sine pi x over L. We know the reason why we have to assume this particular trigonometric trial solution. First of all, the beam bends in a sinusoidal fashion. Okay, it sort of mimics a sine wave, so that makes sense. The next reason is that all these boundary conditions are readily, immediately satisfied by this particular trial solution. So we have got very good reason why we have to assume this particular trial solution. We know that it satisfies the boundary conditions. We have seen that in point collocation method. If you want to try, please try and check it through. Okay, the next step. Second step is usually to apply the boundary conditions. But we know that the boundary conditions are readily satisfied. So I would just write a statement that boundary conditions are satisfied. Usually that is the second step to solve the governing differential equation. Okay, what is the next step? Here we go. The third step is to find d power 4 v by dx power 4. Now, why do you want to find d power 4 v by dx power 4? Because that is what is demanded in the governing differential equation. That is the reason. Okay, here we go. So what is d power 4v by dx power 4? d power 4v by dx power 4. If you differentiate this particular v 4 times, one time differentiation is going to give you a naught sine pi x over L. If you differentiate that, you will be getting cos pi x over L into pi by L. So you have to differentiate it 4 times. So 4 times differentiation is going to give you the value as, here we go, a naught pi raised to the power 4 over L raised to the power 4 into sine pi x over L. So that's good. So we got d power 4v by dx power 4. I will put a tick mark. What is step number 4? Step number 4 is to substitute the value of d power 4 v over dx power 4 in the trial solution, so that we can get the equation for residual. So go ahead and substitute the value of d power 4v by dx power 4. So if you substitute the value of d power 4v by dx power 4 in the governing differential equation, you will be getting ei a into pi raised to the power 4 over L raised to the power 4 into sine pi x over L. So this expression here is ei into d power 4v by dx power 4 minus q naught, that should become 0. In other words, this term should also be equal to q. Rate of loading should be equal to q. But if it is not equal to q, then there is a residual error. We know that it is not equal to q in all the locations. In all the points, we know that it is not equal to q. How do we know? Maybe you can put 0 on the right hand side. For time being, I will put 0. I should not be putting 0. If you are putting 0 on the right hand side, and what happens is, if you work out for a, you are going to get the value of a in terms of a variable. A in terms of a variable, and you have to, which means a in terms of x. And you have to fix that x at L by 2. That is point collocation method. That is point collocation method, which means only at that specific point, this particular left hand side becomes q. This particular left hand side becomes q. At other points, it is not equal to q. There is a residual rate of loading. It should be equal to q, but if it is not equal to q, then it is a residual rate of loading. If this sounds confusing, maybe just pay close attention and listen to this again and again. It will make sense. So right hand side definitely is not equal to 0 except at chosen positions as far as point collocation method is concerned. Okay, now I'm going to erase the right hand side, because the right hand side definitely it is not equal to 0. Okay, so we call this the residual error. Okay, if this is not equal to q in all the locations. Okay, now what is the physical meaning? I have already explained the physical meaning, but anyway, I would like to emphasize on the physical meaning further. So watch it, be patient, and look at the physical meaning. So this is the beam. I'm going to indicate the rate of loading by green color. So this is the rate of loading. Well and good. And suppose if there is a residual rate of loading, I have to indicate that also. So here we go, this red, that indicates a residual rate of loading. That is the residual rate of loading. So that is this unwanted q. So this is q suffix r, the rate of loading that should not exist, but because of the trigonometric trial solution that we assumed, there is a residual rate of loading. I hope you are able to understand this, the physical meaning of the residual, because residual is unwanted rate of loading. Okay, now I would like to emphasize again this point. Let me draw a simply supported beam. Here we go. Well and good. This is the rate of loading. Actual rate of loading is indicated by this green. Okay, well and good. If this is the actual rate of loading, then the deflection of the beam would be something like this. But since there is a residual rate of loading, that is unwanted, irritating rate of loading, then the beam should not bend the way it usually bends, but the beam bends in a different fashion compared to this bending, which is the exact bending. This one is not the exact bending because there is a residual load that acts, not the exact bending. So what do we do? How do we nullify this process? Or maybe I have to use the word alleviate, which means making the problem less severe. So how do you alleviate this particular problem? Okay, here we go. In order to alleviate this problem, this is a simply supported beam. I'm going to draw this again. Simply supported beam. But this time, I'm going to indicate the residual rate of loading. Remember, this is residual rate of loading. If you ask me this question whether residual rate of loading is always UDL, no, it is not. It varies. It may even vary in an erratic fashion, but this is just a symbolic representation. Okay. Now, because of this residual unwanted rate of loading, the beam also bends like this. So this is the unwanted bending due to the unwanted rate of loading. Let me emphasize, this is the unwanted bending due to the unwanted rate of loading. Because of this unwanted rate of loading, residual rate of loading, there is unwanted bending. So what I'm going to do is, I'm going to tell you a statement that there will be unwanted work done. Remember, if there is unwanted rate of loading, if there is unwanted load, there should be unwanted work done. What is the formula for work done? It is force into distance. Work done, unwanted work done. So I'm indicating everything by red. It is force into distance traveled by the force. So that is the precise definition for work done. Force F into distance traveled. Now let us say that the force, unwanted force that is acting on this particular region, let us say that it is unwanted force, which is R, unwanted force, rate of loading, which is R. And let us say that this distance is dx. So what is the unwanted force? Unwanted rate of loading is R. So maybe you can call the unwanted rate of loading R. So I will erase this. If this is confusing, maybe you can call this unwanted rate of loading as simply R. And R into distance, dx, that is force. That is force. Okay. And what is the distance traveled at this by this force? That will be work done. Distance traveled will be V. What is V? It is deflection, unwanted deflection, maybe unwanted deflection. That is V. Now this is an approximation. You see here where we are getting. What I am going to do is, if you just look this very carefully, it is R into deflection into V. But deflection is V. Okay. I will call this deflection W into dx. So I am simply calling this deflection as W. So if you want to find, this is the unwanted rate of loading on this particular small region. If you want to find the unwanted rate of loading throughout this beam, what you do is you integrate. Now what you have to do, you don't want this unwanted rate of loading. So you make the residual 0. I'm sorry, you make the unwanted work done 0. So I have tried my best to give the physical meaning of Galerkin's weighted residual method. So to some extent, I will not say this is the physical meaning strictly, but to some extent, I would say that the physical meaning of Galerkin's weighted residual method, to some extent, strictly speaking, it is not exactly true. What I'm saying here is that the physical meaning will not come for all problems. For example, the thermal problem, if you reflect the same concept, the technique will work, but it would be difficult for you to squeeze out the physical meaning. Okay. Now in the next step, follow from here, it is going to be r into w into dx is equal to 0. But what is this w? I would say w is the same as deflection. What is this deflection? V. And what is this V? It is a sine pi x over L, but I am saying it is a sine pi x over L. But get rid of this a, because even when you substitute a in this particular equation, you take it to the right hand side, it just disappears. So just to make sure that the equations are not getting twisted around, what you actually do is you take this a, even if you substitute the value of a, you take it to the right hand side, it just disappears. So w, we can safely write w is sine pi x over L, because this a doesn't make a difference. Even if you substitute the value of a, it is a constant. You can kind of retract it outside and take it to the right hand side, it just vanishes. So now we know what is w. It is the weighing function. And what is the weighing function? Weighing function is just nothing but the trial solution with the constants removed. So it is the trial solution with the constants removed. So this is the physical meaning of Galerkin's weighted residual method. Now we are going to apply Galerkin's weighted residual method and solve the problem. Okay, let us go to the next page. Here we go. Apply Galerkin's weighted residual method. Galerkin's weighted residual method is saying integral of w into r into dx should be equal to 0, which means you are making the unwanted work done 0. In the next step, we know what is w. It is sine pi x over L into, we know what is r. It is ei into d power 4v by dx power 4. It is a into pi raised to the power 4 over L raised to the power 4 into sine pi x over L minus q, that is r here. So let me indicate that this is this r. Now how do we know that? But if you look back at the pages, we know what is r. We know from this particular equation the value of r, so we got that. And we also know what is w. It is sine pi x over L. So I got this w. It is simply sine pi x over L. So this is w. Into dx should be equal to 0. Okay. Now it is all pure mathematics. You just have to integrate it throughout the entire domain and equate the unwanted work done 0. That is Galerkin's weighted residual method. So let us do it. So in the next step, it is integral over the limit 0 to L. It is ei into a into pi raised to the power 4 over L raised to the power 4 into sine square pi x over L minus q into sine pi x over L into dx should be equal to 0. In the next step, it is integral over the limit 0 to L. It is ei into a into pi raised to the power 4 over L raised to the power 4. Sine square theta can be written as 1 minus cos 2 theta whole divided by 2. Don't ask me how, because I don't have the energy nor I have space on this open board to solve this, to prove this. But you just have to believe that sine square theta is 1 minus cos 2 theta whole divided by 2. So it is 1 minus cos 2 theta. Theta here is pi x over L. So 1 minus cos 2 pi x over L whole divided by 2. That looks complex, but it is actually not. Minus q into sine pi x over L into dx is equal to 0. Okay, in the next step, here we go. So I'm going to take this EIA pi raised to the power 4 divided by L to the power 4, also this 2 outside. Let us see how it will look like. It is EI into A into pi raised to the power 4 over L raised to the power 4. What else we can take outside? Into 2. So I can take this 2 also outside. And I'm going to integrate the first expression. And I'm also going to put integral sign for the second expression so that the mathematics would look conducive. Okay, here we go. 1 minus cos 2 pi x over L into dx minus of, if q is a constant, I can just take it outside. Integral over the limit 0 to L sine pi x over L into dx, that should be equal to 0. Okay, in the next step, it is EI A into pi raised to the power 4 divided by 2, I'm sorry, my battery is running low. Let me try my best to complete this. 2L raised to the power 4 into, if you integrate 1, you are going to get a constant. And if you substitute the upper limit and lower limit, you will be getting L. And integral of cos 2 pi x over L is sine 2 pi x over L divided by 2 pi by L. And if you substitute the upper limit and the lower limit, you are going to get sine 2 pi. If you substitute the upper limit, so sine 2 pi is 0. If you substitute the lower limit, you get sine 0. So that is also 0. So integrating the second term gives 0. Check it through. It's not a big deal. And if you integrate this term here, sine pi x over L, you get minus cos pi x over L. So into L over pi. So I'm doing that right away. It is L over pi into minus cos pi x over L minus cos pi x over L. That is equal to 0. Actually, you will be getting minus cos pi x by L divided by pi by L, but you take this pi by L to the numerator, you get L by pi. That's how you get that. Over the limit 0 to L. So here it is EI A into pi raised to the power 4 divided by 2L cube minus QL over pi. If you substitute the upper limit, you get cos 180 degree, which is minus 1. So already there is a minus sign. So maybe you can take this minus sign, you kind of retract it on the outside so that you get plus. So cos 180 degree is minus 1. Minus of cos 0 degree, that is 1. That is equal to 0. So let us do it. The next page. It is EI into A into pi raised to the power 4 divided by 2L cube is equal to 2QL over pi is equal to 2QL over pi. So work out for A is equal to 4QL raised to the power 4 divided by EI into pi raised to the power 5. So all you have to do is take your calculator and work out the value of 4 divided by pi raised to the power 5. Okay, that is the value of A. Go ahead and do the next step, which is the last step. Substitute the value of a in the trial solution. So the trial solution is v of x is equal to a into sine pi x over l. So now it is 4ql raised to the power 4 divided by ei into pi raised to the power 5 into sine pi x over l. Okay, find out the value of 4 divided by pi raised to the power 5. So what would be that value? So I'm using my calculator. So here we go. That would be 0.01307. So the final solution is 0.01307 into q l raised to the power 4 divided by ei into sine pi x over l. This is fine. This solution is very powerful. The reason why it is powerful is because it goes hand in hand. This solution goes shoulder to shoulder with the exact solution. So you see Galerkin's weighted residual method sort of zeroes in towards the exact solution. In the next session, we will plot the graph and we will see how well Galerkin's weighted residual method is converging towards the exact solution, so that you will be able to appreciate. Radiate hope and do amazing work during this lockdown period. Thank you all for your patience.